Okay, so this talk is inspired by 2001: A Space Odyssey. And so let's get right to it. So some 50 years ago, Arthur C. Clarke and Stanley Kubrick mused at what the near future will hold for regarding human spaceflight. And so while the backdrop of the movie were these eerie alien monoliths created and sent to Earth by an advanced alien civilization, human achievements in the conquest of space was made prominent throughout the movie. And so what we're going to do this morning is reflect on the technological musings of Kubrick and Clarke, and then inspired by the movie and novel, we're going to see how we too can open up the solar system to human settlement, and I will make the case that nuclear energy is key to that. And so what I want to do right now is just reflect on the 2001 universe. What was space travel like in the 2001 universe? So we start first with the simplest, access to low Earth orbit. And so access to low Earth orbit was relatively commonplace in the 2001 universe. You could buy a ticket on a space plane that was commercially operated. Turned out that Pan Am was that commercial vendor. They've since gone out of business. But you could buy your ticket and have the comfort of essentially a jetliner when you go on board, including movies in your seat, just like in aircraft today. The system that they used to launch people into low Earth orbit is this is the Orion 3 spacecraft, but it was a two-stage system. It consisted of a rocket plane and the space plane itself. This system is catapulted into the air via high energy rail, and once it reaches altitude, the rockets of the rocket plane fires, takes it to altitude, and then the space plane detaches and goes into low Earth orbit. The rocket plane glides back down to Earth, is refueled for the next flight. And so it was relatively straightforward to go into low Earth orbit, just buy your ticket. But if you bought a ticket to low Earth orbit, where would you go? Turns out there are multiple destinations in the 2001 universe that you could go to. And one of them was a large space station. Space Station 5 was prominent in the movie. It's a large 300-meter diameter, two-hub space station that was partially under construction, but it also was commercially operated, also by so company on Earth, and Hilton was featured prominently in this novel and also movie as well. You could book your stays at a Hilton, and so that could be your vacation spot in this larger space station. The space station rotated very slowly, about one revolution a minute, to recreate the gravity on the moon. This made your stay more pleasant. You didn't have to worry about motion sickness at all. And so, large space station, access to the space station was readily available. And we have a quick, short demo to demonstrate at least the centrifugal force that keeps people grounded on that space station. And so the weightlessness causes all kinds of health problems. And so a rotating space station creates in the reference frame of that rotating body an effective gravitational force, the centrifugal force, that keeps the person essentially glued to the surface of the space station. And so what I have here is an apparatus with two tubes filled with water, and one side I have a metal ball, and on the other side there's a tennis ball. It's actually stuck in the middle. And so I'm going to spin it and show you that in the reference frame of this non-inertial rotating system, that this ball will feel a very real force that forces it to the outer rim, just like the person is sticking to the rim there. So I'll have to give it a good turn, and you see it immediately spins, and the ball moves to the outer rim. But notice what this tennis ball did. It didn't go to the outside. Now it's at the outside, but when I spin it, it's not at the outside. And I'll let you ask me the question of why that happens at the end of the lectures, because that's something interesting associated with that. But the key point is that the centrifugal force is what allows people to have experience this artificial gravity. Well, what if you didn't want to go just to the space station? In the 2001 universe, there are other destinations you could go to as well, also operated by a commercial vendor, in fact, Pan Am as well. And so Pan Am played a key role in the early part of the movie. And so they had a spacecraft known as the Ares vehicle. In the movie, it was Ares 1B. This was a lunar transporter. It was nuclear powered, had plasma engines, and it would carry you from space station to the surface of the moon. And it was large. It could carry up to 30 passengers. It didn't have artificial gravity on board, but if you read the novel, you'll find at least the bathroom, the toilet seat did have a spinning room so that can, for obvious reasons. But the trip there was only on the order of a day. And so once you got to the moon, you'd want to do something there, right? It's a barren place. But in 2001 universe, the moon was sort of bustling. There were a number of lunar bases on the moon. The lunar base that was prominent in the movie was the Clavius base. It was built in a real crater on the surface of the moon, the Clavius crater. It was a large underground base containing 1,700 people. And to get around on the surface of the moon, they also had transportation vehicle they called the moon bus, which is an all-terrain vehicle, which also had rockets that allowed it to fly over obstacles as well. And this thing could carry 20 passengers. And for all practical purposes, it was its own sort of spaceship. And so the moon was colonized. And the final note as far as space flight in the 2001 universe, it is what about interplanetary space travel? The book makes it clear that humans had already gone to Mars, and Mars also was essentially settled, but they hadn't reached out much farther than the asteroid belt. And so the book and movie takes place, they were written concurrently. It takes place with the humans building a spaceship and getting ready to go to Jupiter. And this crown jewel spaceship is called the Discovery 1. And it's a pretty awesome vehicle, and we'll talk about it. It was 520 feet long, nuclear powered, and it had a habitat module that rotated. It also produced 1/6 gravity of Earth, so lunar orbit, lunar gravity. And you can see those people on the side there. They was people in suspended animation. So also suspended animation was featured in the movie as well. In addition, there was artificial intelligence that was the caretaker of the ship. Actually, it was the only thing that knew. It alone knew the true purpose of the mission for the Discovery 1. And we'll play a sound clip of that thing in a second. But what's important about the Discovery 1 and what's sort of like the launching point of this particular talk are the propulsion systems. It turns out that Kubrick and Clark pondered on what propulsion systems should be used to carry the vehicle from Earth to Jupiter. And so it turns out these engines include the ones that they discussed was a nuclear electric propulsion device known as a magnetoplasma-dynamic thruster. So long, I just put the MPD there. Nuclear pulse propulsion and gas core fission engines. And we'll talk about each of them. And I guess as this is our jumping off point from 2001, no 2001 talk would be complete if we didn't listen to Hal, the artificial intelligence that descends into madness during the movie, and they have to shut it off in the movie. And for some reason, I can't crowd that. Here we go. Thanks, Monica.
I know that you and Frank were planning to disconnect me.
Well,
and I'm afraid that's something I cannot allow to happen.
Okay, let me play that again. Go back. Oh, too much. I don't have too much. So here we go.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
And so it goes mad and tries to kill everybody on the spaceship. And then the movie proceeds from there. But but artificial intelligence was prominent in this time period. And so how do we match up with the 2001 universe? Well, so we don't have access to space for regular citizens unless you may be a billionaire. We can't We're not sending 20 passengers up at a time. But we do have commercial access to space from a standpoint of delivering cargo and cargo both to the space station and also satellites into low Earth and geosynchronous orbit. So we do have commercial vendors, and it may be around the corner when we're actually sending people for space tourism. But where do those space tourists go? Well, we don't have a space station like Space Station 5, but we do have an international space station that's a laboratory for microgravity. There's no artificial gravity on this. The sole purpose is to study microgravity effects. This space station houses 6 people and has habitable volume of half the volume of a 747. So it's much smaller than Space Station 5. But we do have a space station, but it's not a vacation spot at this point. But they're supposed to commercialize it at some point, and who knows. So as far as interplanetary transportation system, or even a near Earth space transportation system for humans, we haven't developed that yet, but we are working on it. NASA's developing the Space Launch System, SLS. It's going to be a big rocket, a little bit more powerful than a Saturn V, and it'll support human operations near Earth and also to the surface of the moon and perhaps even to Mars. And so that's coming along. But so far, nothing like a Discovery 1 where we can explore other planets. And what about the moon base? Well, interestingly enough, we did go to the moon, and we went there multiple times, but we didn't establish a moon base. We do have the capability of going to the moon, but we didn't get the base. It's not unreasonable for Arthur C. Clarke and Kubrick to think that we would have a moon base some 30 years after we were supposed to land on the surface of the moon, but that just didn't happen. But this does bring up another interesting question about space, and it's important to talk about it before we talk about developing an advanced system to send people to other places in the solar system, and that is why do we want to do it in the first place? Why do we want to send people into space? And so it turns out there's some very real reasons why we would want to start settling the solar system. And so I list some scary things here, such as overpopulation, scarcity of resources, pandemics, this dinosaur-like events, asteroids, catastrophic wars. So all of these are potential problems. But what's interesting is that one can argue that technology may be able to buy us out of some of these problems. But if you think about it, as you propagate deep into the future, let's say technology helps us avoid these things. We can, as our population grows, we start using more and more of the surface area of the Earth. Eventually, we start colonizing the surface of the sea and also the bottoms of the sea and extracting resources from those. Then we go to the polar region and start colonizing that. So at some point, we will have covered all of the surface of the Earth, right? And we will have tapped out all the resources on the surface of the Earth. So what then do we do? So we'll be at some precipice of some kind of extinction event if we don't spread out. So at some point, deep in the future, we have to leave Earth. We have to become a multi-planet or multi-moon species. But space is hard. It's NASA lists all the risks to space. There's weightlessness in 0G. There are physiological problems such as cardiovascular. Your skeleton, your bone loses calcium. Muscles degrade, immune systems degrade. This is where the 2001 universe kind of had it right. Having those rotating systems, you produce artificial gravity. Then there's psychological problems associated with isolation. It's interesting, in the 2001 universe, it was the artificial intelligence that ended up having a psychological problem and moving around into people. And this is a big one, radiation risk. But it turns out that radiation risk are probably one of the biggest threats to us spreading out. If you look at this little inset graphic here, it shows the radiation that we get on Earth due to radiation emanating from outer space. And it's relatively small. That's our natural background radiation. Earth is naturally radioactive. But if you go into space, you get a factor, interplanetary space, you're talking about a factor of almost 100 times that amount. And this can be particularly problematic from a health standpoint. And so where does the radiation come from? Well, there are essentially 3 sources of radiation space. One is the sun. It's constantly spewing out energetic protons and electrons, and at times these can be super energetic. These cause coronal mass ejections and solar flares. Then you have the Van Allen belts, and we'll show a chart of that next. But Van Allen belts capture some of those particles from the emitted by the sun on our, basically the Van Allen belts are our magnetic field lines loaded with energetic particles. And those are stuck there, and a spacecraft has to pass through those in order to leave Earth. And finally, there's the galactic cosmic ray. And galactic cosmic rays come from outside the solar system, and they're particularly dangerous because they're very high energy and very difficult to address. Normally, radiation workers address radioactivity and radioactive sources in three ways. You maximize your distance from the source, you shield yourself, and you minimize your time around the source. Well, in space, you can do some shielding, but with galactic cosmic rays, they're so penetrating that it's very little you can do to attenuate those energies. Some particles, a single particle can have the energy of a thrown rock. It's a single charged particle. And then, so shielding is probably out. Distance. Well, you can't distance yourselves from galactic cosmic rays because they're coming from outside the solar system, so it's isotropic, they're coming from everywhere, so you can't distance yourself from. So the only thing we have is time. Time meaning we can develop fast rockets to reduce the transit time from one point to another. So if we want to settle space, we need to have fast rockets so we can limit our radiation exposure. You know, what's interesting is that this, that my mouse arrow disappears over the pictures for some reason, but the picture on the left bottom side is film that was carried by Neil Armstrong when he went to the moon. Basically, the lines that you see are tracks of radioactive particles that was passing through his body. And as you can see, the activity is quite significant. The thick line is a representative of a very heavy ion passing through. So basically, during that journey, they were peppered with energetic particles because the shielding wasn't there. On Earth, we are protected from a lot of this radiation. We have two force fields, basically. As I mentioned, these Van Allen belts are associated with our magnetic field. So Earth has a dipole magnetic field, and this magnetic field captures the charged particles from the sun, and those particles are stuck on the magnetic field line, and they just bounce from one pole to the next. They're stuck there, but astronauts have to pass through this, and that's a problem. But for us, it's good because it's shielding us. Our atmosphere also protects us from cosmic rays as well. Solar particles have low enough energy that they can actually be captured by our magnetic field. But galactic cosmic rays are energetic enough that they can pass through this force field and end up interacting with our atmosphere. And so, in doing so, they generate a secondary shower of energetic particles that is greatly attenuated by the time it reaches the surface of the Earth. And so, for us, our radiation dose from these cosmic rays is low but measurable. For astronauts, though, in interplanetary space, a third of all your DNA is going to be sliced every year as you on transit. So this is a problem. And it turns out these remnants of these cosmic rays that are passing through our bodies now, we can actually see them in a device called a cloud chamber. And so on display should be the cloud chamber coming up. At some point, but there's a cloud chamber. So what is a cloud chamber? A cloud chamber is a container that contains supersaturated vapor. And so when a cosmic ray passes through the cloud chamber, it generates an ionization path. Ionization attracts vapor molecules, and they form basically little droplets or little clouds. And so they end up looking like little contrails. And so if you look at this, you're looking in real time at cosmic ray activity and also a little bit of radioactivity that has been inserted into the cloud chamber using a thoriated tungsten rod, which produces helium nuclei that pass through. So all the particles that seem to be emanating radially from that rod that you see are from us, but any other little track that you see is associated with cosmic rays. And as you can see, as Monica said, it's an active day for cosmic rays. And it's not surprising, though, because we're in solar minimum. When you're in solar minimum, we get a larger cosmic ray dose. And so the fact that, and so this is what we're getting here on Earth in interplanetary space, orders of magnitude, the tracks would just overlap. And so we have to get from point A to point B as fast as rapidly possible. And And so we need fast rockets to do that. And this is where advanced technologies take place. So we'll review rocket equation really quickly. So the rockets that we use these days are still based on Newton's third law. We haven't perfected wormholes yet. But when we do, we reset. But right now, we're stuck with the balloon analogy, blowing out mass to produce action-reaction. So mass is blown out one direction, the vehicle feels a reaction force and moves in another direction. And so this is Newton's law of force equals mass times acceleration. If we solve that equation, we come up with the rocket equation. And so this is the only equation in the whole talk. So the change in velocity of a rocket is proportional to the natural log of the mass of the rocket before the fuel burn of the mass of the rocket after the fuel burn. So the difference between mass before and after is the fuel that's expended. U sub B is the exhaust velocity. If you transpose this equation, you get the following expression. It's an exponential that helps illustrate the rocket equation a bit better. And so first I should tell you that delta V is important in space science because in order to get from one point to another point, you have to speed your rocket up. You have to undergo a velocity increment to go, because you could think of the solar system, the planets are at certain energy levels. So in order to get from one energy level, Earth's orbiting around the sun, to say Jupiter, you have to increase your kinetic energy. It's a gravitational well. And so the farther you're out, you go, the larger that delta V, which means that your mass required to do that mission grows essentially exponentially. The only knob we have to put this in check is the exhaust velocity. So you notice the exhaust velocity is in the denominator here. So the larger the exhaust velocity, the smaller this ratio will be. And so in practice, we like the exhaust velocity to be large compared to the delta V of a particular mission. Some other parameters of interest for rocketry is thrust. Thrust is a product of the mass flow out times the exhaust velocity. And another parameter that characterizes a specific impulse that is closely related to the exhaust velocity is the specific impulse. Specific impulse is a ratio of the thrust to the mass flow out of the device. And it's a measure of rocket efficiency. So you can think of the specific impulse as the thrust you get per gallon of fuel you expend per unit time. And so it's essentially the thrust per gallon. So the higher that number is, the more efficient the engine is. And advanced rockets have specific impulse in the thousands. The units are seconds, of thousands of seconds. Chemical rockets in the hundreds of seconds. So it's almost a factor of 10 different. And if we plug in the definition of thrust into this equation, we get some cancellation. We see the specific impulse, the efficiency is proportional to the exhaust velocity. The importance of high exhaust velocity is also shown in this next graphic. It shows that if you have a conventional rocket, a chemical rocket, which produces low thrust, and an advanced rocket, I'm calling it electric rocket here, we compare them. So they both want to go in the same delta V. But because the exhaust velocity of the chemical rocket is smaller than that of the electric rocket, you need more propellant, more fuel in order to do the mission, which means that you have smaller space for payload. You have much larger space for payload, people, equipment, machinery, if you use advanced rockets. So there's another benefit for having fast rockets as well. And so where do we go once we've developed an advanced rocket? Well, it turns out there are a lot of interesting places in the solar system to go to. In 2001, they were going to Jupiter. It took about 2 years it was going to take 2 years for a round trip to Jupiter. Interestingly, in the movie, they were going to Jupiter. If you read the book, though, they were actually going to Saturn. They were going to pass Jupiter and go to Saturn and then be picked up by another vehicle, the Discovery 2, at Saturn, which is interesting. But that's not in the movie. But even though they were just sort of written at the same time, it's just kind of weird. The novel and the movie aren't exactly the same. And so there are a lot of interesting places in the solar system to go. And in my opinion, there are even more interesting places to go than just Mars. I think Mars is overrated. But so look at so if you go to Jupiter, look what you have. You have an ice ocean of Europa. You have Ganymede and Callisto. all icy moons, and Europa may have life in its ocean. And then if you go to Saturn, you have Titan. Its atmosphere is thicker than Earth's. Can you believe that? You can float down to the surface, and Titan's atmosphere is so thick. It is so far away. It's a moon. And then Enceladus at Saturn, which is an icy worldless world. And even Neptune's Triton also has ice. So these are places that we can colonize. How long does it take to get to these places? So this is a bit of a busy chart, but it describes the so-called Hohmann transfer. So to get from point A to point B in the solar system most efficiently, meaning to use the smallest amount of fuel, you execute the Hohmann transfer. And so I'll sort of walk you through and have a graphic as well. But so assume this center dot is the sun, and we're in orbit around the sun. And so the Hohmann transfer, and we want to get to this orbit. Let's say this is Mars. So the Hohmann transfer involves doing a fuel burn to get on a transfer ellipse. And once you're on the transfer ellipse, when your transfer ellipse is tangent to the orbit of the planet you're trying to get to, you do another burn. And usually this is a reverse burn because you're usually coming in hot with too much excess kinetic energy. And then you go into orbit around the planet you're trying to get to. And so the reason why I show the Hohmann transfer, because it is the most efficient way to get from point A to B, but unfortunately it's also the slowest. But it does give you some perspective on how long it takes to efficiently get to these planets. And so note that Jupiter, the delta V to get to Jupiter, total delta V is 8.8 kilometers a second, and the trip time is 2.73 years. That's one way. And remember, in 2001, the round trip was 2 years, so much faster. But the number I want you to remember is 8.8 kilometers a second because it'll come back up. And here's a graphic of the Hohmann transfer, but using it to change orbital position. So here is our little spacecraft. This thing will start over. So it's orbiting Earth. It wants to go to a higher orbit. And to do so, it's going to execute a fuel burn to get on a transfer ellipse that's tangent to the orbit it wants to go to. And then it does another burn to circularize its orbit. So that's all there is to the Hohmann transfer. Most efficient way to do it, but it's also the slowest. But it does give us some perspective on how long it takes to get from point A to point B. And we see that we're talking about years of exposure. That's why we really need fast rockets, because with a fast rocket, you don't have to do a Hohmann transfer. You can almost do nearly straight line transfers. And so how do we provide energy to the thrust-producing plume? Well, there's just three ways to do it. Is chemically, that's the way we do it these days. Electrically, more and more we're seeing these plasma rockets. And nuclear, we don't have any nuclear rockets flying right now. But it turns out that the thrust power, the jet power in the plume, the exhaust velocity, all proportional to the energy density of the fuel. So the higher the energy content of the fuel, the more powerful your rocket will be. The higher the exhaust velocity, the higher the thrust density. And so for a relative scale, for chemical rocket systems, the energy content is about 40 megajoules per kilogram. And this turns out to give you a theoretical maximum from thermodynamics of exhaust velocity of 5 kilometers a second. There are no rockets flying right now that have 5 kilometers a second. It's more in the order between 3 and 4 kilometers a second. And so remember, to get to Jupiter, it's 8.8 kilometers a second. So that's a number that's considerably larger than the 3 kilometers a second, which means that you're going to need a lot of fuel in order to get to Jupiter, almost too much to be practical. That's why we're not talking about sending people to Jupiter with chemical rockets. In fact, we're talking about Mars a lot, so a fast piloted 60-day round trip to Mars. I mean, normally, if you look at the books, it's over 2 years, just 2 to 3 years just to do a round trip to Mars, because you have to wait till it comes back around. And so you could, with high energy density systems, you can do 60-day round trip missions. So this chart is somewhat busy, but the idea is that these nuclear fuels here are able to deliver large amounts of payload to Mars, or even do one-way trips to Alpha Centauri in under 50 years because of the energy density, energy content in the fuel. And so some missions you can't even consider doing without considering a high energy density fuel such as fission, fusion, and one-day antimatter. The fact that nuclear energy is enabling for interplanetary flight was recognized even by Robert Goddard back in the old days, he made this quote. He said, and this was in the early days of understanding radioactive decay, the navigation of interplanetary space depends on a solution to the problem of atomic disintegration. So he knew that those particles in atomic disintegration had high energies, which means that that could be high exhaust velocities for him. And so he was excited about that way back then. So he's sort of a visionary. So what are these nuclear processes that of interest to us for propulsion? So this is a review. So fission and fusion are the two processes that are being investigated, or that are being, from a conceptual standpoint, for propulsion. And they also show up in 2001. So what is fission? Fission is the neutron absorption of a fissile nucleus. That's one that goes unstable when it absorbs a neutron, I'm sorry. And so when it goes unstable, it eventually splits into two nuclei, and along with neutrons, gamma rays are also released. But what's interesting about this process is that all of the particles that are released are high energy. They have high kinetic energies. And so the neutrons that are released have the capacity to interact with adjacent nuclei and cause them to split as well, resulting in an enormous release of energy. So this simulation shows chain reaction taking place, those excess neutrons driving the fission process and releasing a large amount of energy. The second process is nuclear fusion, and it involves the fusing of two light nuclei together to form a heavier one. And in the process, this also releases large amounts of energy. And you might ask, well, where does the energy come from? Well, if you weigh the products and you weigh the reactants, it turns out the products are lighter than the reactants. That missing mass is converted into the kinetic energy of the particles via Einstein's famous equation, E equals mc squared. And so if you look at the nuclear stability curve, nuclei that are low in mass can gain higher stability. If you fuse them together, you move up this chart. Nuclei that have high atomic mass numbers, if you split them, they form species that have higher stability as well, or higher binding energy. And so they are energy releasing. So any physical process that gives you, any nuclear reaction that gives you more stable nuclei are energy releasing. So fission splits heavy nuclei, fusion merges light nuclei. And so this is, I like this graphic. This was provided to me by George Smith at NASA Glenn Research Center. But it puts into perspective the comparison between chemical energy, fuel density, and nuclear energy density. Even if you don't even pay attention to the bar graphs, and just look at the bottom, 50 external fuel tanks of a chemical rocket, the space shuttle's external engine, the space shuttle's external fuel tank, 50 of them is equivalent to a single Coke can of uranium-235. And if you want to get really crazy, one day we'll be able to make antimatter, but you need only 3 raisins of antimatter to have the equivalent of that, and that is impressive. And so the nuclear, just the energy content allows us to do a lot. And so we're about to go into the rockets shortly, but just want to tell you, so we're ready for this nuclear age. There are 4 ways to couple that nuclear energy into the fuel. One way is to use it as a heat exchanger. Basically, the nuclear reactions can be used to thermally heat your fuel up. You can use the nuclear reactions to heat a plasma up and let that expand out of a nozzle. You can use your nuclear energy released to just produce electrical power, and that can run a plasma rocket. And the final way is that the nuclear particles, those energetic particles, expand out of a magnetic nozzle to produce thrust. And we'll talk about that one shortly. There's another reason why we want to use nuclear energy to explore outer planets in particular is simply the fact that solar can only take you so far. You can see here, for reference, Earth's, at the top of Earth's atmosphere, the solar radiance is around 1,400 watts per meter squared. When you get to Jupiter, that's down to 50. Saturn's 15. If you're talking about Pluto, it's virtually nothing. And so in order to have power out here, you need a nuclear power source. You can't use solar rays. It'd be impractically large because the solar intensity drops off as 1 over r squared from the sun. And so we need we need nuclear power. And so let's finally bring on the rockets. And so if you dig around, you find that when they were developing the screenplay for 2001: A Space Odyssey and developing the novel, they were considering three propulsion schemes. One is magnetoplasma-dynamic thruster, the other is nuclear pulse propulsion, and the final one is the gas core fission thruster. And so we're going to go through each one of these propulsion schemes, because it turns out that NASA had been researching these propulsion schemes in the past, and they were aware of some of this research. Because if you could perfect these propulsion schemes, you could open up the solar system to human spaceflight. And so let's talk about the magnetoplasma-dynamic thruster. It is a plasma rocket, and so what we want to do is first just review the 4 states of matter. So let's just do this really quickly. So you start with a solid, you heat the solid up, you get a liquid, you heat the liquid up, you get a gas. You heat the gas up, to a large degree, you get this superionized state called a plasma. Plasma is a quasi-neutral collection of electrons and ions with the capacity for collective motion. So the electrons are no longer bound to the atoms anymore. You have just ions and electrons. And because they're free like this, you can use electric and magnetic fields to control those particles, do work on them, and to produce thrust. And so how do we make plasmas? Well, the most basic way to make plasmas is to apply voltage between two closely spaced electrodes. And I'm going to just crank this plasma up over here. So you have two closely spaced electrodes in a rarefied atmosphere, some 10,000 to a million times below atmospheric pressure. When you apply the voltage, if it's sufficiently high enough, it will break down, forming a plasma. And the plasma almost always starts by seed electrons formed by cosmic rays that pass through the gas. And so they produce an electron. Electrons accelerated produces another electron-ion pair by ionization. So 2 electrons become 4, 4 electrons become 8, and so forth. So you end up with an avalanche in the plasma. And as you increase the voltage, if you look here, you can see the length of the plasma column increase. So you're making more plasma. You're driving that ionization process. And so that's the way plasma rockets work in general. You apply voltage and you make a plasma. Then you have to do work on it to make the thrust. And so plasma rockets fall into a category known as electric propulsion. Electric propulsion is a facet of rocket science that deals with those engine systems that generate thrust by electrical means. And so what's nice about electric propulsion is that the propellant and the energy source are separate, so I can arbitrarily add energy to my propellant to do work on it. I can make it into charged particles and then accelerate those particles to produce thrust. These systems can produce exhaust velocities 10 to 100 times that of chemical rockets, but the thrust that they produce is low, and so they can only be used in space. You can't take off from the surface of the Earth. So now, finally, our first thruster. So the first engine that was of the ones that we're going to talk about today, that was considered for 2001 is the magnetoplasma-dynamic thruster. We just call it an MPD thruster. They are the highest thrust density of all the plasma rockets. They, if you get them to work, they can really open up the solar system for human and robotic exploration, particularly to the outer planets. But these systems don't operate efficiently until you're operating in the hundreds of kilowatts to megawatt range. And so let's take a look at how MPD thruster work. So I have two diagrams. One's an old NASA graphic, and the other one is one from Scientific American, which came out about 5 years ago. So it's an annular device, so it's an annular anode and a rod cathode. If you apply voltage between the two in the presence of a low-pressure gas, such as hydrogen, you get an arc, but not just any arc. It's a high-current arc, thousands of amps, and associated with that arc flowing through the cathode is a magnetic field that's in the azimuthal direction. In fact, if you point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. The thumb has been pointed in the direction of the conventional Ben Franklin current, which is positive current flow. And so what you notice right away is that the current flow is essentially perpendicular to the magnetic field. And this gives rise to a magnetic force on the plasma that blows it out of the device. So currents in radio. This is radio current. The magnetic field is in the azimuthal direction. Thrust is in the Z because you're blowing the plasma out of the device in the Z direction. So it's basically a plasma blower, but it does so efficiently. And we do have a demo that illustrates this operating principle for a magnetoplasma dynamic thruster. And so I have a graphic up here as well. You probably remember current carrying wire in a magnetic field will experience a force that's proportional to the current, the length of the wire, and the magnetic field. And so what we have is a demo. This is going to be my plasma. Plasmas can actually have conductivity. Electric conductivity is higher than metal. And so in this apparatus, I have a rail that when I place this rod on the rail, it completes a circuit. So voltage is applied across the rail. And so I put it here. If I press this button, current will pass through this rod. Now, along the track is magnets. And the magnet is pointing in the vertical direction. So magnetic field's in the vertical direction, current's is perpendicular to that. So what direction should this be blown or moved? Yeah, that's right. Either up or down, depending on the polarity. And so I'm going to put it up here, and we'll see. So this is plasma, and this is our MPD thruster, and we'll see it. So it flies slowly and flies out and produces thrust. So that's the basic concept of MPD thruster. But an MPD thruster is happening continuously, and the currents are not like amps here, but thousands of amps. So you can get high thrust. These things were extensively researched in the 60s by NASA. Here's one. They envision using these to take people to Mars. Your nuclear reactors on the end here, and this is a spacecraft, and this is a plume. This is one on a test stand at NASA Glenn Research Center, and this is a plume of an MPD thruster. So they have a lot of capability. The problem with the MPD thruster is what researchers found, and even associated with my thesis research, is that MPD thrusters, most of the power that you input into the device ends up deposited into the anode of the device. And so if you're running at a megawatt and you're depositing 50 to 60% of that into the anode, it's going to melt. And so it has no lifetime. So electrodes, lifetime was a problem, and power deposition was a problem. And that's why it's still in the research state. Until you solve those problems, we can't use it. And, but if you did solve those problems, you would need to run one of these engines with a nuclear reactor because they only operate efficiently at hundreds of kilowatts or megawatts. And just as a fun fact, the United States was the first to launch a space nuclear reactor in space. They did it actually in 1965. And so we did it in 1965, and we haven't done it since, which is interesting. And that reactor worked. So this is a mission study from NASA using an MPD thruster to go to Jupiter, just like in 2001. And it's actually for people. This is a human mission to Jupiter. It would feature a 12-megawatt system, 6 MPD thrusters. The total thrust would be 408 newtons. And you would be able to get to Jupiter in only 24 months. So 2 years, basically. That's still under the Hohmann transfer, but that's not bad to get to Jupiter using this propulsion scheme. So it does have some possibilities, but we have some technical challenges. The next propulsion scheme is a bit more controversial. It's the nuclear pulse propulsion scheme. And so it involves detonating low-yield nuclear bomblets downstream of the vehicle, and the momentum from that will push you along. And you just do this repetitively. And the program by which this was under which this was studied is Project Orion, and it has its sort of history dating back to the late 40s. This program died eventually in the mid-60s, but they did quite a bit of mission studies showing that it's viable. What really killed it was the test ban treaties for testing nuclear warheads in outer space. But this was supposed to be a peaceful use for nuclear warheads. I have a graphic here of a test the United States carried out, Starfish Prime, back in 1962, of a high-altitude nuclear detonation. When they did that test, they were unfamiliar with the electromagnetic pulse. And so electromagnetic pulse did happen and knocked out some communication satellites. We didn't have many back in '62, but they paid for that one. And Hawaii suffered a partial blackout. And so if you use a nuclear pulse type propulsion scheme, you have to use it far away from the Earth. And we'll talk about it next. But I do want to point out that Arthur C. Clarke was a big fan of nuclear pulse propulsion. In fact, he wanted it to be the main propulsion for the Discovery 1. But Kubrick was against that because of the Test Ban Treaty. And he also had the Strangelove movie, and he just didn't want that all mixed together. Just see, he had an obsession with nuclear warheads. But you can deliver a lot of cargo anywhere in the solar system using nuclear pulse propulsion. So how does it work? So this graphic shows how nuclear pulse propulsion systems work. So basically there are two variants. You can detonate the little low-yield nukes inside of a combustion chamber and let the exhaust products fly out to produce thrust. That doesn't work so well, so you have to have a working fuel to couple that energy into, and then that'll produce your thrust. These systems using fuel like that to couple into still had performance only twice that of chemical, so not so good. What worked the best was the use of a shaped nuclear charge and detonate it 30 meters downstream and let the explosion push against a physical pusher plate. And we actually have some models of this design on the table, and you're welcome to take a look at them after the talk. But these, you could achieve specific impulses 10 to 100 times greater than that of a chemical rocket system. And this is the concept that was used this was a concept that was studied in detail on the Project Orion. Project Orion had its history way back in the days where we were doing nuclear tests. The first test was this Viper experiment, where they detonated, they placed two spears, graphite coated, above a nuclear warhead, 20 kilotons, and they detonated it. And they were able to recover the spears several miles away, and but they weren't destroyed. Only a millimeter of ablation. So it says that the pusher plate concept can work. And then there was additional test back in '59 where they tested stability of the vehicle behind those explosions, and I have a little movie to show for both of those. But first, as far as the concept goes, the rocket would look like this, and this is how it would look if it were flying through space, basically detonating and pushing against a pusher plate with shock absorbers, because you have people in there, they have to survive each one of those heavy G's, and that's and so that's that. But it turns out that and this thing is in the Smithsonian. They did a test of this using chemical explosives to see could you propel a vehicle into to high altitude. And so this thing, so this is the device returning back to the surface. It's on a loop. So here it goes. It's going to take off on a series of little explosions, fractions of a second apart. But the flight was stable, and they were able to reach 100 meters with this, and this also validated the stability. And so the idea was that this could be the basis for a transportation system to get anywhere in the solar system. And all you need is just repetition rates of one explosion per 10 seconds or one explosion per second. And the yields would be quite low as well for the nuclear warheads. Standoff distance between 30 and 300 meters. And so NASA eventually took over the Project Orion, and they were developing concepts to put this, to use a Saturn V to launch this thing into a high orbit, and then it would take off. They would use it to go to Mars with round-trip times on the order of 240 days. So you can do a lot with a propulsion system like this, but with the Test Ban Treaty, it was essentially a non-starter, so this program was canceled. And what took its place was a more kinder and gentler version of nuclear pulse propulsion. And this involved nuclear fusion of hydrogen fuel pellets. And so in this case, you use fusion, that energetic plasma produced in the nuclear fusion process would push against not a physical plate, but a magnetic nozzle, and that would produce your thrust. And so the basis was inertial confinement fusion. You use lasers to initiate the fusion event. You use lasers to compress a fuel pellet to fusion conditions. And I have a little video of that process here. So this is from the National Ignition Facility at Lawrence Livermore National Labs, and this is the way they do this inertial confinement fusion process to release energy from hydrogen fuel. So you have a fuel pellet, like you see in this graphic, and it's placed inside a gold canister. The fuel pellet is only a millimeter in diameter. And so you illuminate the walls of that canister with lasers, 192 lasers, that vaporizes the walls, producing recombination plasma that makes X-rays. And those X-rays uniformly compress the pellet to fusion conditions. So you inertially compress and heat to the point before it falls apart to the fusion condition, and you get the large energy release. And so a vehicle for interplanetary space transportation applications was developed based on that inertial confinement fusion concept. And the idea is that this vehicle would have on its bottom a magnetic field coil, and you inject pellets and use lasers to fuse those pellets to produce the fusion fuel. That fusion plasma will rapidly expand and push against the magnetic field and push you along. So it's still this sort of putt-putt type propulsion, but in this case, it's fusion plasmas that are being that's pushing against you. And the repetition rates for this is much higher than hertz. It's hundreds of hertz. And we have a demo that demonstrates this propulsion scheme here. So it's a ring launcher, and I have a diagram for the ring launcher. So what we have here is a magnetic field coil, and this is going to be the field coil associated with the rocket. And this is metal. Again, it's going to simulate our plasma. And so the way it works here is when I flip this switch, the coil is activated. That produces a time-varying magnetic field, which generates an eddy current inside this metal. And that's going to produce its own magnetic field that's in repulsion against the applied magnetic field. And so when I apply this, this thing is going to shoot up, and I will try to catch it. Oh, it went way up. Okay, so I caught it, and that's so the eddy current also forms inside the plasma. It's called diamagnetic current, and that is the basis for its propulsion. And it sort of looks like this. It's very slow graphic here. So lasers, and it pushes the vehicle out of the way. But this propulsion scheme is, if you run the numbers, do the mission analysis, you can beat 2001: A Space Odyssey as far as round trips to Jupiter. This is 422 days round trip to Jupiter. So this propulsion scheme, very energetic, featuring nuclear fusion. You can open up the solar system to human exploration. The problem is we haven't been able to get the inertial confinement fusion process to work correctly. It's still a problem. So I'm going to try to run through the rest of this fairly quickly now. So just want to make a comment that in the 70s, the British Interplanetary Society developed a propulsion system based on this as well. And the goal was to get to Barnard Star, which is about 6 light years away. And they would use many tons of those pellets in order to get to 12.2% the speed of light. And that would get them there in 50 years, one way, but in orbit around our star. So that's a true starship. So the final propulsion scheme that we're going to talk about, so I have about 7 minutes on the clock here, is nuclear thermal rockets. And so in the 60s, NASA developed to a high state of readiness the nuclear thermal rocket. A nuclear thermal rocket basically utilizes reactor heat to heat the propellant to produce thrust. And so I'll describe how it works here. So they developed this in the 60s to support human missions to the moon and Mars. But the problem was that after Apollo was canceled, this all was canceled as well. And so it features a nuclear reactor that's basically contains graphite fuel rods with particles of uranium-235 embedded. These fuel rods had channels which you could pass hydrogen gas through. If you place those rods, gang them together in a critical assembly with a reflector nearby, it becomes a fissioning reactor and produces a thermal energy, heat. It heats up. So if you pass the hydrogen through it, that hydrogen gas will heat up and expand out of the nozzle to produce thrust. With hydrogen, you can do twice the efficiency of a chemical rocket. The problem with this system is that this is good for Moon and Mars, but the specific impulse of 1,000 is not so great to go to Jupiter. The limitation of this propulsion system is the reactor. You can't run graphite much above 4,000 degrees or it'll melt. And so that's your limitation. But what if you didn't have a solid reactor? What if your reactor was gaseous? If your reactor was gaseous, uranium-235, basically a uranium-235 plasma sun, you could run it at not 4,000 degrees Kelvin, but 40,000 degrees Kelvin, or even higher. You can heat that hydrogen gas to temperatures at your specific impulse could be 5 to 6,000 seconds specific impulse, greater than any system that we have today. And the thing about these engines is not only do you get high exhaust velocity, you get high thrust as well. In fact, Arthur C. Clarke was such a fan of the gas-core nuclear reactor, he made the following comment in his Promise of Space: if the engineering problems associated with building gas-core reactors can be solved, the economics of space flights would be totally transformed. The whole of the solar system would be thrown open to humankind if we could figure out how this thing works, if we can get it to work. And they've been working on it since the 60s. So, but it has some problems. So I'll name those problems and we'll go ahead and wrap up. And so the biggest problem is confining this 25 to 30 kilogram ball of uranium plasma hydrodynamically, because it's floating, right? And this gas is flowing by. So the idea is to generate a vortex to confine this uranium plasma. And so that's one problem. And so if you want to get it confined, you also don't want it to shoot out the back. Because if uranium plasma shoots out the back, when you accelerate, it's gone, right? There's no more thrust. And then you got pollution as well. And the other problem is that so you can heat the gas to really high temperatures, but that hot gas has to pass through a nozzle, so you can melt the nozzle as well, and that's a problem. Also, transferring the energy from this uranium plasma to the gas is tricky too. But it turns out that hydrogen gas absorbs UV light. If the gas is at 10,000 degrees Kelvin, it's emitting mostly UV light, and that means that the hydrogen will readily absorb that and heat up to high temperatures. And so there are a lot of technical challenges associated with it, but if we could do it, we can open up the solar system to exploration. These are mission studies from NASA. They're not talking about Mars. They're talking about Jupiter, Saturn, Uranus, even Neptune. And all of these are round-trip times of less than a decade with 200-day stays. So the whole of the solar system truly could be opened up if we could perfect the gas-core nuclear rockets. 80-day courier transports to Mars, delivering large amounts of payload. So, to close it all out, we ended with with 3 propulsion systems that have been researched by NASA in the past, and it was considered for 2001: A Space Odyssey. And it turns out if we could get any one of them to work, we could open up the solar system to true human exploration and settlement. Because at some point we have to consider settling the outer planets, because we can't be just a one-planet people. And then we too can realize our own space odyssey, and that's it.